Monomeric G-actin or globular actin is a 42 kilodalton protein that tightly binds one ATP and one divalent cation in a cleft between two large domains. G-actin is box-like in shape. The square front face has dimensions 55 by 55 angstroms squared, with a width of 35 angstroms. For clarity, we represent each amino acid by a single sphere 5 angstroms in radius. In the presence of salt, the actin polymerizes into a helical assembly called F-actin or filamentous actin. The helix is built by translating a monomer 27.5 angstroms and then rotating by minus 166 degrees. Since the angle is close to 180 degrees, F-actin looks like two slowly intertwining helices. Typically, thousands of monomers polymerize into filaments tens of microns long. Here we present the normal mode analysis. There are 6 continuous curves in the dispersion plot for the fiber. Here's the stretching mode. This mode pertains to an acoustic longitudinal stretching wave. It is seen to have a very long wavelength. The torsion mode. This motion, also having a small frequency, is readily activated. It is easy to see the long wavelength torsional waves propagating along the filament. The bending mode. This mode, having a small frequency, is easily activated. This motion is seen to pertain to a long wavelength bending of the polymer. The axial slipping mode. This motion, typical to the intertwined actin helix, shows an axial slipping motion of the two long-pitched strands. This is a result of relatively weak binding between the long-pitched strands. Note that even though the wavelength of this motion is very short, the correlation length of the motion extends over the entire length of the filament. The groove swinging mode. Another motion typical of actin is characterized by a rolling motion of the strands to produce an alternate opening and closing of the groove angle. These computer animations convey the character of the computed motions much more clearly than inspection of the components of the eigenvectors. The analysis must be generalized to include the effect of internal monomer flexibilities and solvent. We have previously computed the normal modes of the actin monomer and are incorporating this information into the analysis of F-actin dynamics. The atomic model of filamentous actin was developed by Ken Holmes based on X-ray fiber diffraction images of aligned gels of the filaments, using the atomic structure of G-actin as a model for the monomer.